Okay, thanks, thanks Herb for a nice introduction. And this is thanks for sticking with the conference to the end. And, and this is a really tough act to follow after 3 terrific talks, and especially after they keep saying, Jeanie will tell you this, and Jeanie will tell you that. So I was, as they speak, I was taking out slides that are redundant, and putting in slides that they say they promise. In the end, I gave up. So I'm just going to, give a talk. So this is, this is a long day. This is going to be a really light talk. So I'm just going to talk, it's a little bit in general about nanotechnology, and in particular graphene. Okay, so nanotechnology 101, what is nanotechnology? I'm sure I don't have to tell this crowd. It's just the creation, control, and manipulation of matters on the scale of 1 to 100 nanometers. How big is a nanometer? Nanometer is 1 billionth of a meter, 100,000th of the width of the human hair. And you'll say, okay, that all sounds really small, but I still don't know how small it is. Okay, so we can try this way. So you take a basketball and blow it up to the size of the Earth. And the buckyball, which is here. Where's my buckyball? Here. The buckyball is 1.1 nanometer in diameter. So the same scale of blowing up, it's basically the size of a tennis ball. So that's really pretty small. Okay, so here's a look at scale of things. So we can start with kind of human hairs, which is kind of smallest thing you can see with naked eye. And then you go down a few orders of magnitude, go down maybe 100 times in diameter. You have spider silk and blood cells. And bacteria is about 200 nanometers. Virus is about 30 nanometers in diameter. DNA is about 2 nanometers in diameter, in width. Okay, so these are pretty small. And if you consider atom-to-atom distance in the solids, they are 0.3 nanometers in diameter. So in 1 nanometer, you can fit maybe 3 atoms in between them. And atoms, of course, are really, really small. And, well, okay, we'll skip the protons. Okay, those are the high-energy physics, which we don't try not to work with. Okay, so we say, all right, so the next question is always, why should we care? Okay, so, all right, I prepared several answers. The first one is, because it's there. Okay, because it is at the limit currently of human knowledge. It is fun to just push the envelope of the knowledge a little bit more, to learn more at this fundamental length scale. It's actually a strange length scale because, you have huge objects. It's actually very well described by Newtonian mechanics. And if you have very, very small length scales on the order of high energy physics, actually a lot is known about them. Actually, they know their mass, they know the interaction, et cetera, But on the order of, this length scale, when you have hundreds or thousands of atoms, actually very little is known about them. And what we always say, in condensed matter physics, when theory agrees with experiment within factor of pi, it's good enough. So that's what we're talking about. So actually very little is known about when you have this complex interaction of a large number of atoms that described by quantum mechanics is actually a very interesting problem. Okay, but okay, pushing human knowledge, people, okay. All right, so that's the next question. Next answer I prepared is given by J.J. Thomson, who discovered electrons in 1897. So this parliament member asked him, is there any use for those electrons? Okay, so his answer is, I don't know, but I'm sure you'll find a way to tax it. Okay, so I think graphene, nanotubes, I don't know, but I think they'll find a way to tax it too. Okay, all right, if that still doesn't satisfy whoever asked the question, all right, here's, then we can always fall back to nanotechnology, which is, of course, starts with this talk by Richard Feynman, who gave a talk, really visionary talk in 1959. He titled There's Plenty of Room at the Bottom. You probably heard about it. Actually, I heard about it until I didn't realize how visionary it is until I read it in preparation for this lecture. Actually, so he said, what I want to talk about is the problem of manipulating control things on small scale miniaturization. He said, all the information accumulated by mankind can be written in a Q material or 200th of an inch, etc. There's plenty of room at the bottom. And then he go on to make predictions. Why can't we make the computing machines very small? At the time, they occupy rooms. Why can't we make the wires 110 to 100 atoms in diameter? And they say if we have millions of the computing elements, the computer can make judgments. Okay, so that's kind of started a revolution of first micro and nanotechnology. This is Moore's law. Okay, it's not a law of nature. It is possible because lots of physicists, engineers, and material scientists have been working on this. So it's coined by Gordon Moore, the Intel founder, who said the number of transistors on integrated circuit doubles every 18 to 24 months. So they start with kind of moderate number, 8,000. So on an integrated circuit, it's about maybe size this big, right? Maybe an inch or so. So you have 8,000 transistors on them. And then you can see now it's actually already 2010. You have a few billion transistors on a size of this big. You think about it, it's amazing, right? You can fit, every man, woman, and children on this world. If you imagine shrink them down, and it can fit into something about this size. And each of those little person, and do computation. Okay, so that's an amazing feat achieved by the industry. Okay, and so another version of the Moore's law is that the size of transistor reduced by 30% every 1.5 to 2 years. And so you can see it's basically actually 2010, 2011, it went down to already 22 nanometers in size. So you will look at the scale of this naturally occurring things, there's the man-made things. So basically start out the Intel chip in 1980. It's like a little bit smaller than human hair, but still larger than the bacteria. The Intel chip last year, actually 2 years ago now. Now it's already comparable to the size of a virus. Okay, so it's so each of those computing elements is the size of a virus. Okay, so this is another perspective we can see to what we have done in the past 50 years. This is one of the world's first computers, calculators. It was actually in display at Harvard Science Center. It fills a room. It's 10,000 pounds. It performs 9-digit multiplication in 6 seconds and costs $500,000 in today's money. And of course, everyone knows what we have now, right? We have an iPhone, which is much smaller, much lighter, and with gigahertz of computation speed. It's a camera, it's a phone, it's a music player, it's a GPS, it's a calculator, it plays games, and it keeps track of phone numbers. It's like extended brain of ours, right? And it's only $300 only. But so this is huge progress we made, and all because of our relentless effort to make things smaller and smaller. Okay, so here's the prediction that Feynman has made in 1960. So they said at the time computer room size, he thinks we can make this much smaller. Now they are, of course, pound sized. They said the wires at the time was about the size of a human hair. And he said they can be 10 to 100 atoms in diameter. Actually, now that's 22 nanometer size. It's actually about only 60 atoms in diameter. So it has been achieved. They said at the time you can only do simple calculation. So Feynman said computer can run the judgment. Of course, we have Watson, who actually won the Jeopardy. I think he can probably, before long, is going to probably take all our jobs away. Okay, so this is a very nice law. So of course we wanted to continue to for another, if we can, for say another 20 years. But so you can see that here now it's reaching the size of atoms, reaching the size of single atoms, reaching the size of buckyballs. So and then when things are that small, a lot of things to happen. You can have charge leakage for example, you cram so many, 10 billion transistor size this small, and each of them crank out doing the computation. They need to take power. The power dissipation becomes larger and larger in the chip that's small, and that's why your laptop becomes hotter and hotter, right? So how to remove the heat efficiently? It's a problem. Then at this length scale, also quantum mechanical effects start to set in. Then you can have charge leakage. You can have so the little wires, and it's you face a current carrying limit. You cannot carry a lot of current because it's just like little fuse, so it will blow up. So it's many challenges when we try to make things smaller and smaller. Another thing that you can see as a challenge, but from a physics point of view, I think it's also a very interesting opportunity. Is that there's a lot of unexpected phenomena just arising from confining electrons and atoms to this nanometer scale, the so-called low-dimensional physics. And those interesting properties, just fun to understand and to study it. It's like a gift from nature to tell us something. But it's also maybe when we really understand this phenomena, we can make use of this phenomenon to fabricate new devices. Okay, so that's some sort of motivation. So we are looking at the length scale of atomic length scale here. Okay, so let me just go talk about graphene now. Graphene, we already heard 3 talks, so I don't need to say too much about it. So graphene is basically, maybe we can just pass this around. Graphene is a piece of, so it's a carbon atoms arranged in the honeycomb lattice hexagonal structure. So it's flat, and it's a good electrical conductor. Then you can stack them up to form graphite. You have 2 pieces of graphene. Imagine this goes to many, many layers. You can have them to form graphite. Okay, and it has been dubbed as the mother of carbon allotropes. If you roll it up, you can form this is so-called zero-dimensional buckyballs. Okay, zero-dimensional because it's small on all 3 dimensions. Okay, so it's nanometer scale in all dimensions, so we call zero-dimensional buckyball. Okay, and you can roll it up to form a carbon nanotube. Okay, we call this one-dimensional conductor, one-dimensional material because it's only long in 1 dimension, okay? All the other 2 dimensions are small, so it's 1 dimension. And the graphene itself is 2 dimension, okay? Because it's long in 2 of the dimensions, but very, very tiny thickness, okay? And then we can stack it up to form graphite. Okay, this is a C28, which is also kind of, I just made it. Okay, so a brief history of graphene. All right, let me skip this really fast. The first was made used to mark sheep, okay, and then it was made used to make pencil, and then it's industrial use. Actually, there's a lot of industrial use for graphene for steel making crucibles, lubricants, etc. So in the 1947 theory of graphene, of electron movement of graphene was already discussed. So from the 60s to 90s. Actually, the people find there is nuisance of monolayer graphite found on metal surfaces at high vacuum. And so Eva can probably tell us this, but they find this very, very, very annoying because they really just want to study the metal surface. Okay, we'll come back to that later. So from 1995 onwards, there's an attempt to make graphene with very, very fancy techniques, like push it around with this atomic force microscope, really tiny tip, and try to push things around. There's various degrees of success. Of course, in 2004, Professor Geim and Novoselov at Manchester, they used a scotch tape technique. Okay, so we already heard about it, and the rest is history. Okay, so there's a huge, since 2004 to 2005, there's a huge increase, sudden increase in the number of papers. This is the physics preprint server where people post the results on there. So with keyword graphene, you can increase this almost exponentially, and this is resulting in a huge bandwagon. Okay, so this, so lots of people start to get on board. Okay, so physicists, chemists, everyone. So sometimes I do feel like this guy is like, okay, get on. Okay, and of course in 2010, these two guys, Andrei Geim and Kostya and Novoselov, won the Nobel Prize. Okay, so we already know. Okay, so this is the Nobel winning experiment. We already heard about it. We basically just take a piece of graphene and kind of rub it, right? So it's like pencil writing. This is 1, 2, 3 layers of graphene, and this is thicker layer. So you can tell the number of layers just under optical microscope. So this is actually amazing. You think about it, you can actually see the single atomic layer of something. Okay, this is the largest piece of graphene we had in my lab, a millimeter squared. This is a piece of my student's hair. So he's so proud that he wanted to put the hair just in comparison, on the same scale. Okay, and so graphene, as we know, is 2-dimensional, and so this is not a new system. Because it actually has been the favorite system for physicists to study for actually a very long time, past 30, 40 years. The thing is that all these typical experiments require very expensive equipment. So for example, molecular beam epitaxy costs about $1 million maybe $2 to build. Okay, and you have to do things with it using scanning electron microscope. So graphene, that's why it's so great, is that we replace that with a scotch tape. We can replace that with a good optical microscope, right? So it makes things a lot easier, accessible for physicists worldwide. And because those expensive equipment also takes years of training and really, really difficult to make. There's only a few labs worldwide making those type of systems, and you have to know one of them, or be good relationship with one of them, send them gift from time to time. Well, I'm just kidding. But you do have to have access to those very, very specialized training to produce 2-dimensional system prior to graphene. So graphene, you call up the company and say, hey, I need some nitrographic samples, and they send you a bag free of charge. And you start rubbing. Well, hire 20 high school students and start rubbing. Okay, but on the other hand, it's also the most expensive material ever. We have invented in 2008. This was first pointed out by Titov. He's now at University of Edinburgh. So this graphene industry, I believe, is actually located in Manchester. So they sell graphene materials, and it's taken from the website. Its pricing guide is about 1 micron square per pound, and if you do the math, okay, the cost per gram is 10 to the 15 US. Okay, so then this will cost of a bailout is only 700 billion. Okay, it's really chump change compared to that. National debt, chump change. Okay, so if we can only if we can make the payment in graphene will solve all our economic problems. Okay, so that's so yeah, well, our millimeter square size sample, it's actually worth $1 million. Anyone interested, you're welcome to contact me after that. Okay, so it's a big bandwagon. It's been evolving both in terms of science and technology. I'll talk a little bit about science, a little bit about technology, but mostly the science. Okay, so why is graphene the physicist's favorite toy? It's a truly 2-dimensional material. So there's a nice review article, Physics Today, written by Professor Geim, Professor McDonald, talking about graphene flatland. Another thing which really immediately captured people's attention is the electron loss and mass in this the sheet. I think you already heard talks about it, so I'm just go through this really quickly. But I do want to show this, which is Big Bang theory. I can't believe no one has shown it before, but so I just have to show it. Oops, sorry.
To engage the superior colliculus of my brain. Einstein. I usually just have coffee. You've been up all night?
Is it morning?
Yes.
Then I've been up all night.
And you're stuck?
Why else would a person try to engage their superior colliculus?
Sorry, sweetie, I can't help you till I've had my coffee.
Benny, I told you, if you don't put him in his crate at night, he just runs around the apartment.
What is he doing now?
He's either isolating the terms of his formula and examining them individually, or looking for the alligator that swallowed his hand after Peter Pan cut it off.
Captain Hook's hand was eaten by a crocodile, not an alligator.
Okay, so the idea is that Sheldon, the string theorist,
How has he been stuck? Intellectually about 30 hours, emotionally about 29 years.
okay, so get this on. The Sheldon Cooper, the theorist, the string theorist, have trouble. He's really vexed by the problem why electron loss at mass. Okay, so well, I think Professor Geim and Professor Andre already explained it very nicely, so I'm just going to skip through this. So this is equal to mc squared. If you basically get rid of the mass, the energy will be proportional to the momentum, and so this is why it's called the relativistic particles, because the energy is just simply proportional to momentum, and like massive particles, where energy is quadratic in momentum. So that's so that's energy momentum relationship. It's linear. Okay, so that's why electrons in graphene act as massless relativistic particles. So one of the consequences of that is that the so-called Klein tunneling, which is relativistic particle that pass through a barrier perfectly. This is like graphene quantum cars that you already seen the animation about. So it's predicted by Oscar Klein, a Swedish physicist. So the problem is this was predicted for high energy physics, but so it's thought to be realizable only at the edge of black holes because it requires enormous electric field. So, but graphene, it's a piece, you get graphene from the pencils. So I like to tell my students that whenever you write, you are making black holes for the electrons. Okay. So the graphene is actually electrons in graphene just can basically, this has been verified, you can go through the barrier perfectly. Okay, so what does my group do is I'm mostly interested in electrical transport spectroscopy. Okay, that sounds like a bit jargonish. So what does it mean? It just means we measure its resistance. Okay, so then your next question is, do you really get a PhD for doing that? Okay, so but you actually do. It's actually a very powerful tool to study the electronic states, the spin state, electron phonon interaction, etc. You can tell whether electrons act up charge. Particles or waves. You can study the transport of heat or energy. And it's also an art to fabricate and locate graphene, and you have to make something this tiny, right? 1 atomic layer thick, and connect to your hand that you can turn a knob on something to change its property, right? So that's not easy. Now I have to perform the measurements, and the hardest part is to figure out what the data tell you. Okay, so how do we do it? You cannot do this. Okay, if you do this in my lab, I have to kick you out immediately. So first is we rub it. Okay, so this is a $1 million piece. And then look at it under the optical microscope. The next thing we do is to make a graphene transistor, meaning we put electrode on them. So here's basically you would put the electrode, and next time I'm going to tell you how we put the electrodes on them. So this is so basically a piece of graphene, you put the electrodes and then connect up to a battery. And so this part we call it the source. You can just imagine it's like force that you think you're injecting the electrons. And this part is called a drain. So you it's like a drain, you drain the electrons. Basically so that basically push the electron through from one end to another. And then you have something called a gate, which is basically like the gate. You turn this knob on the gate. This controls the total number of electrons on graphene. You can change the total number, and you also can change into conducting by, say, electrons are holes, white holes or blue holes. Okay, so this is, in this case, that's why we make a graphene transistor. Okay, so how do we attach the electrodes? After all, graphene is only one atomic layer thick. It's not very big, and even the width and length are not very large. So this is something called, we use a lithography. This is so-called lithography printing. Well, you all know what lithography is, right? People have been doing this for ages. What you do is you put one type of lithography anyway. You put the wax layer on the plate and use the knife to carve the pattern on the wax. You pour ink so that this will stain where the pattern is, and then you remove the wax, and this will give you the pattern. So this is something we do very, very similar, so-called lithography. This is the same technique used by semiconductor industry to make all the computer chips. You just on a little bit smaller scale. So what you do is so-called you put the wax layer on the plate. The wax is just some sort of, here we use some sort of polymer. Okay, and then we use light of electrons instead of knife. We use light of electrons because they have very small wavelength. So they're equivalent to a very, very fine knife to carve the patterns on the surface. So here's so put the so-called resist, and then you put the light of electron to pattern it. Basically, this polymer has property that when the light of electron hits it, it goes away. And then we can then you pour ink. In this case, we put white metal on top, and then you dissolve this wax away, or the so-called lift of it. You dissolve the resist away, and you're left with this little pattern, a patch of metal on the surface. So this is a piece of graphene, and these are the electrodes. So this whole thing is maybe 10 micrometer long. That's how we make the tiny little electrodes on there. Okay, and then we measure the devices at low temperature in so-called helium-3 fridge. The liquid helium-3 boils at 3.2 Kelvin. They actually manufacture for nuclear reaction. It's actually was actually a crisis in the United States for some time ago because there's not enough helium-3 going around. And then we evaporate helium-3, so it's like evaporative cooling. We evaporate it goes down to about 0.25 Kelvin. So this is what I like to tell my students. It's actually cooler than outer space. So it's cool, literally. Okay, so then now we have a graphene device. So we call it bipolar field effect transistor. So this is what you have. So on the left side, it's so-called hole doped. So you can think about this as like hourglass. On this side of the gate voltage, the electron. So it's so-called P-type of hole doped. On the right side, you can fill the electron up to here. Then it's electron doped or N doped. And so on the middle, it's so-called the direct point of the charge neutrality point. It's like a glass half empty, half full kind of scenario. So that this is actually where the point is really interesting physics happens. So the conductivity goes more or less linearly with number of electrons. And also amazing thing is that you can carry really high current density. You can carry about 1 microamp per atomic row. So it's really, this is, I think, the kind of a record of what can be carried. So no other material have shown this. And so it's about 20 times more conductive than silicon. Okay, so this is some of the data from my lab. This is one of the first things we do. We put the graphene, and then we measure conductance as a function of bias voltage, which is the voltage applied to that battery, and the function of gate. So this is basically our way of looking at 30 megabytes of data at the same time. You plot the conductance as a function of color. And so then you have this three-dimensional plot. So here basically the red is high conductance and yellow is low conductance. And you look at this, hopefully you can immediately see, or I can immediately see, that there's this kind of checkerboard pattern, right? So there's oscillations. If you go horizontally, you can see red, yellow, red, yellow, red, yellow. And go vertically, it's also red, yellow, red, yellow. So which means conductance oscillate as a function of gate voltage or the bias voltage. And this similar thing has been seen in nanotubes. This is data. This is not simulation. This is just a really very, very, very nice sample. You can see this really nice checkerboard pattern in nanotubes too. Okay. So what this happens is that what we have is so-called some sort of interference effect. The electrons are basically waves in graphene, so they're reflected back and forth between the electrodes and interfere with each other, so they form standing waves. And what happens when you change either the gate voltage, which changes, or change the bias, actually both change the kinetic energy of the electrons, and that actually will change the wavelength, because you change the energy, you change the wavelength, and therefore the standing wave pattern changes. You're going through interference maximums and minimums, and that's why you have this kind of oscillation in conductance as a function of in both bias and gate voltage. So this is we call it a quantum billiard. So it's like a playing billiard board. Basically, the balls are the electrons. The graphene is a table. The electrons kind of zooming around inside on graphene, but they kind of reflected by the boundary or by the electrode. But what makes it quantum is that here the balls are just classical. They're just the balls, the particles. But in graphene electrons, they are also quantum. They are also waves, so the waves can interfere with each other, and so you also can see this get this type of patterns. Okay, so I just have to show this again.
Cheeseburger, breaking 2 Jewish dietary restrictions
All right,
simultaneously.
Let me maybe. Wait just a minute. Okay, maybe I'll just play it like that. Okay, I'll play here.
Order.
Sheldon doesn't work here.
Is that really necessary?
Oops. Oh,
Sure.
just missed a good part.
The motion of the wave to the molecular...
Honey, not to complain, but we were starting to think you didn't either.
Is that really necessary? Good Lord. The interference pattern in the fracture. The motion of the wave to the molecular structure. I've been looking at it all wrong. I can't consider the electrons as particles. They move through the graphene as a wave. It's a wave! The moment to applaud would be now. Troglodytes.
Sheldon, where are you going? Aren't you going to clean this up?
I'm sorry, I don't work here. Right, one
Oops.
bacon cheese.
Okay. Okay, so so the idea is that Sheldon really stuck on working on the problem of massless electrons, and so he has to take up some manual job to liberate his subconscious to work on this tough problem. So I finally figured out electrons in graphene waves. So happy to report that I did not have to do that. Okay. So and then that's a very nice. That's a nice demonstration of the interference effect of electron waves in graphene. Oops. Let me go through that. Okay, so what can this lead us? So one of the things is so-called electron optics. For example, we can explore the wave-like nature of electrons in graphene. We can control the electrons like optics. For example, we demonstrate a Fabry-Perot resonant cavity, which is optical cavity, and Philip Kim's group at Columbia had demonstrated, for example, the p-n junctions spaces for some sort of lenses. This is They can use that to, for example, focus electrons, make electrons instead of, right now electrons are sort of go everywhere. They bounce out when they hit the defect or hit the boundary, but maybe we can use it so we can, for example, focus electron like we focus optics and make it go, use interference effect. Okay, so graphene also have amazing mechanical properties, which you already heard very nice talk from Jim about that. I'm going to skip this. It's very strong and tough. It's very elastic, and it's very soft. Okay, soft in the sense that because it's two-dimensional material, even though it's very hard to stretch it this way, it's actually very easy to bend it. Okay, because it's only atomic layer thin. So this is one of these experiments that grow out of our kind of failed attempts. It's one of those accidental discoveries. So for example, we try to make suspended graphene devices because they're free of substrate, they're very, very clean. So we tried a few things. What we want to do is we basically just we make trenches on the substrate on silicon wafer, and then we directly deposit just again, 5 undergraduates rub graphene across the trenches, and we find them, we deposit electrodes, and then we find they have actually very low mobility, and what we think is, what the heck is going on? Okay, so this is me, I'm saying, huh? And my student just say, okay, we are lost. Okay, so this is the thing is that, well, the case we try to figure out what's going on that leads to some really interesting discovery. Is that when we try to start to image, to look at our devices, look at these graphene membranes across the trenches under SEM, the scanning electron microscope. So this is a piece of graphene. These are the trench. So this substrate is a little brighter. So it's graphene covering most of the image here. You just look it down, really downward, and you see this is really just normal piece of graphene. You tilt it to 45 degrees, you're looking at partially at edge. It's still really normal piece of graphene. But then you tilt it to very high angle, then you start to see this kind of fringes forming. Okay, so these are very, very periodic fringes. And you sort of look at it almost from the side. So what are those? Those are actually ripples. So they actually spontaneously form ripples. And this is some SEM, another electron image. This is AFM. Again, Jim talked about using this tip. This atomic force microscope. Using tip go through, and you can actually measure. You can actually look at the profile of these ripples. They are actually really sinusoidal, forms this kind of sine shape. And so here's another one. This is actually the edge. So here the tip goes into the trench. So this is just really beautiful pictures, at least. Okay, so really fun thing to look at. And at the time, it's also very surprising because people's conception is that graphene is very rigid, as shown by Professor Hong before. It's very, very rigid material. It's very strong, very rigid material. So why would you form the ripples? It actually turns out to be understood by just so-called physics of wrinkling. It's actually a basic competition of you get energy by you want to stretch something, so you can either stretch it, but then it's so stiff you try to, then it goes up to the third dimension. You actually see it in everyday life. I don't know, this is a good demonstration. You take a piece of Saran wrap and then you stretch it, and you see the ripples start to form, actually somewhat periodic, right? So that's but this is nice physical review. I'd like to talk about this to actually explain how wrinkles form around the eye first, and how the eye post dried out and have those wrinkles in the eye post skin. That's a really nice piece of article. So we find this, and we can explain our data perfectly. And so this is the illustration. And the take-home message is that graphene is the thinnest Saran wrap. We all have done this, right? This is you scale everything down to a single atomic level. This is actually a really ugly piece of graphene device, and because the trench is really ugly, it's just a bad sample. But you can see this irregular ripples form because it's pinned by these rugged edges. And but if you can pin everything and stretch it, so then this is what you have for the single atomic version, a single atomic layer version. So this is after this, we never look at Saran wrap in the same way in the kitchen. Another really interesting thing about graphene, actually you can probably, another Saran wrap physics, if you take Saran wrap and put it in the microwave or put it in the oven, what will happen? It balls up, right? This is actually exactly what happens to graphene. So this is when we heat it up and cool it down again, we see the ripples will change, and sometimes they actually, so they either have larger amplitude or wavelengths, or sometimes they actually either buckles upwards from the little tunnel or goes downwards, sags into the trench. And so this is, this here's a movie of, oops. Why can't I? Okay, so here's this electron microscope movie showing a piece of graphene over the trench, and when we heat it up to 200 Celsius, it was flat, and you cool it down, I hope you can see it becomes wrinkled. So this is just like you take a piece of graphene and tightly over a piece of Tupperware, and then you heat it up and cool it down again. So this is our, again, graphene version of that. You see this very nice periodic ripples forms around this square, this hexagonal, and the circular hole. And you can also see that the ripples are all aligned perpendicular to the edge. So depending on what your edge is. So this is basically just the attempt of the membrane to release a strain because from this thermal expansion. So what happened is the graphene has actually so-called negative thermal expansion. It just says that when you heat it up, you actually contract. When you cool it down, you actually expand. So it's one of those strange things that behave contrary to what you would expect. But if this happens in all two-dimensional material, for example, in a Saran wrap, it happens like that too. And so because of this large difference in the thermal expansion coefficient between graphene and the substrate, so then when you cool it down again, graphene, so they try to release the strain by forming the ripples that are perpendicular to the edges. So this is another really kind of a really interesting piece of physics. Again, in everyday kitchen, you don't think too much about it, but then we actually start to understand it from the atomic version. Okay, so why is that interesting? This is because graphene really has a double identity. It's a really great conductor, have all these amazing electronic properties. It's also thinnest isolated membrane, and you don't have any other system like that. So maybe we can control that, combine the two. We can explore electrical properties of ripple graphene. And this is because when you start to make the atoms go out of plane, depending how you make them go, those orbitals start to arrange themselves. You can actually change the electrical properties by doing that. So the shape actually does have an effect on the electrical properties. For example, insulating diamond, conducting graphene. So there's actually various predictions that, for example, you can produce effective local magnetic field, or even electric field without external field, meaning making a graphene go in certain direction or go in circles without actually having to apply this kind of electric field, magnetic field externally. So this will be, of course, really, really interesting. And these are some of the, there's a lot of predictions by the theorist community. It's a little harder to see experimentally, as usual. As usual things predicted by theorists. But this was maybe last year or a year and a half ago. So this very nice paper from Berkeley talking about strain-induced magnetic field greater than 300 Tesla in graphene nanobubbles. They were able to create this triangular-shaped nanobubble and determine that it's actually have electrons on this bubble experience magnetic field that's equivalent to 300 Tesla. So that's this gigantic field. If you don't know or don't already know, the highest magnetic field, at least steady magnetic field on Earth, is about 45 Tesla in National High Magnetic Field Lab, which actually I'm going there next week. Try to use. Well, I can only access to 30 Tesla field. So about a factor of 10 smaller than this. So this is one of the first demonstration of the string-based engineering. So based on this, we can probably, there's a lot of things to go by engineering the shape, etc. How am I doing on time? 2 minutes. Okay, really fast. Okay, bilayer graphene. So now we say, why do we start with single layer, go to bilayer? Bilayer is actually, it's interesting for its own sake. For example, we want to open a gap in digital electronics because single layer graphene is gapless. Bilayer, although, but by applying electric field, we can open a band gap. Another interesting thing is the fundamental understanding of nature. For example, it's possible we can to see the spontaneous symmetry breaking in bilayer. This is similar mechanism of Higgs bosons. So again, last week's conference, we're debating whether we're going to have a bet whether we'll see Higgs boson before the high energy community do. Okay. Why stop at 2? Then we go for 3, 1, 2, 3, infinity. So trilayer graphene is actually interesting. Let me just go through this very quickly. This is another one of those accidental things we discovered when we started to measure trilayer graphene. This talks of conductivity as a function of mobility. Mobility roughly measures how clean the sample is, how well the electrons conduct. Oops. Okay, so then we actually have lots of samples. What we see is that so these are the different stacking. I'll tell you what the stacking is. What we find that is that it looks like there's very obvious 2 groups of samples. So these are very high quality samples, and you can see some of them are conductive and some of them are just insulating, right? So this is conductivity is almost 0, and then we thought it's really strange, and we go back and find that they're actually due to a stacking order. Okay, so what is a stacking order? So you can consider the single layer graphene. So you have this honeycomb lattice. Basically, from physics' point of view, this honeycomb lattice consists of 2 interlacing triangular lattices, and each of the triangular lattices is considered to be different. So therefore, we call it A lattice and a B lattice. So indicated by this red and the blue dots. Okay, so and then if we add another layer, the most stable way is to the so-called Bernal stacking or AB stacking, which you put one of the sublattice, so say the red dots, inside the honeycomb lattice, okay, and the other one just stacks up on top. But this blue one stacks up on top of the red one. Okay, then you add a 3rd layer of graphene. There are 2 ways of stacking it now. So you can stack it as a so-called ABA, which means the top layer is just exactly the same as the bottom layer. This red one is exactly on top of the bottom layer, the red one on the bottom layer. Or you can shift it by just single atomic distance, shift the whole thing so that the top layer and bottom layer also forms the AB stacking. So this red ball on the top layer is now on top of the blue ball of the bottom layer. So this is called ABA and ABC stacking. It's a little bit dragonish, but actually they actually have very different electronic properties. You just look different. I can tell you in detail if you're interested. So basically what we do is you can just shift the top sheet by 1 atomic position, that will cause a change from an insulator to a conductor. So that's actually amazing if you just think about it. And if you go even up further to n-layer graphene, then actually there are 2 to the power n minus 2 different ways to stack the layers. So bilayer is only 1 way. 3 layers, there are 2 ways. We go to 4 layers, there's 4 ways to stack it. And they each have different band structures. So perhaps we can change the electronic property by stacking, if we can find a way to change the stacking. So this is actually really interesting. So let me skip through this. So this wonder material, it's 2-dimension, it's compatible with silicon technology. It's stronger than silk, softer than silk, conducts heat better, conducts electricity better, you can carry a lot more current without burning up, and it's also transparent when you look around. For example, most transparent stuff are actually insulators. For example, plastic, but graphene is a conductor and transparent, so chemically stable and inert. So it just there's a lot of fascinating physics in there. That's what keeps the physicists interested. But it also holds a lot of promise for post-silicon electronics. I think some of this application already. So for example, maybe we can replace silicon, although this is still a tall order, so people are working towards it. One of the really probably a really immediate application is for graphene to be used as transparent electrodes for touch screens, solar cells, LCD displays. It can be, for example, chemical-mechanical sensors, energy storage, and one of this interesting thing from the Ruoff's group at Texas. For example, they take a piece of this penny, U.S. penny, they coat half of it with graphene, and half uncoated, and they stick it in the oxygen furnace, and they come out. This part is still shiny, and the other part is completely tarnished. So this is really great single atomic layer anti-oxidation film. This because it's so impermeable to other materials. Okay, so this is expired. Okay, so people are making large-scale graphene synthesis. I think Jim already mentioned it. So it's actually still a lot of challenges in this field, but I want to show the more slide of graphene. We have made huge progress in past 5 or 6 years. This is mobility value, which measures how clean or how good the device is, goes up by 100 times, where size of graphene made is already went up by 10 to the power 5, 100,000 times. So it's amazing progress. I think it's only a matter of time before we overcome these challenges. Okay, so I want to thank my collaborators and also my students, funding support. Okay, so let's.
Okay, we have about 5 minutes for questions and discussion. I see someone in the back there.
Yeah, I'm curious with the rippling effect. Do you think you could physically constrain and only allow it to ripple in a certain space? So if you only allowed like one ripple to pop up in a certain space, then you could have only graphene up in that area, and then it's conductive there, and then it's not in the spaces you don't allow it?
What's outside the rip? Yes, I think theoretically, yes, you can do that. There are various ways. So we're trying out, actually, we and other groups are trying to do that. The thing with graphene is, I guess, it still conducts outside the ripple region. The question is a matter of fact how much it conducts, or can we engineer the string in such a shape that make it go only where we want it to go. So, for example, if there's a prediction probably that if you can make the string have a triangular shape, for example, you can create the magnetic field, and the electrons will just go in circles. So if we can demonstrate that in electrical measurement, I think that would be really cool.
Yes, you had one chart indicating there was electromagnetic interference. Now, is that indicating that it's susceptible, graphene is susceptible to electromagnetic interference?
Oh, I don't. Did I say that?
It was an earlier chart.
Are you talking about the electronic interference?
Yes.
So that's just this is just only about electrons in graphene acting as waves, so they're bouncing back and forth and interfering with each other. And when we can observe this wave nature of electrons in graphene in the experiment. So I think it has nothing to do with electronic interference. You talk about electromagnetic interference. But regarding that question, there are actually also proposals, I think, from Samsung about using graphene as a radiation shield, because it's very, very thin and it's conductive, and it also have all the other wonderful properties of being stable, being inert, being transparent, and you can use that to guard, for example, sensitive electronic equipment inside.
Well, you're talking about going down one order of magnitude smaller in substrates. So you would have more interference if you can use graphene as an insulator. It'd be solve the problem.
Graphene is conducting, unfortunately.
Well, it can also be used as an insulator, right?
That's one of the grand challenges, billion-dollar question this whole field is trying to answer is how to make it insulating. Or better yet, how do we control it so that we want it insulating sometimes and not insulating some other times. It's a knob we can turn to make it that way. That is a billion-dollar question. If you answer it, you'll be rich and famous.
I'd like to ask you, you had a 300 Tesla magnetic field. Two parts to my question. One, how do you measure it? And the second thing is, how do you really model the creation of it? Is it just because it's a massless fermion, and you're looking at a magnetic moment due to that?
Okay, so that's a very good question. Why? Let me just show you. It's not really. It's pseudo-magnetic field, so it's not real magnetic field. When they call about it's okay. It's okay. It's probably easier we go this way. What it basically it's only describes the effect on the electrons. Okay, so this is pseudo-magnetic field. Okay, so it's not real magnetic field. It only describes the effect on the electrons. For example, electron in a magnetic field will go in circles, and this will do that. And there's also other property. I think Professor Ivan Andre talked about earlier about the electron orbit in high magnetic field will form the so-called Landau levels. There was something special will happen, and that's how they measured it. But they were able to tell from the spacing between energy spacing between the Landau level follow certain rules is proportional. Well, in this case, it's actually determined by the magnetic field. By measuring those Landau levels, they are able to tell it's equivalent to 300 Tesla magnetic field. But it's not saying that you can levitate something. Okay, by putting this something above this bubble. It's not. It's only the effect on the electrons inside graphene. They are under the equivalent influence of 300 Tesla.
So are there any other questions or comments? Okay, if not, let's thank our speaker again.